in section 10 of chapter 14, Klein's Organic Chemistry textbook, it's a very important part of the chapter. It's about 7-8 pages long, and this is where your organic chemistry professor is going to emphasize things. You want to review SM1, SN2, and stereochemistry, okay? We have an epoxide that's going to have some stereochemistry associated with it, and we need to be able to recognize R and S stereogenic centers, assign the configuration using the Ingold-Prelog rules, okay, to see if it's R or S. We're going to react these epoxides with strong nucleophiles, which react by SN2. Remember, with SN2, you get inversion of configuration at the actual bond, at the actual carbon that's undergoing bond breaking and bond forming. For weak nucleophiles, those proceed by an SM1 reaction mechanism, and those will cause racemization of the carbon that's being broken and formed to new bonds, new atoms and groups, okay? And the reason why is the planar carbocation can react with the incoming nucleophile from either face. So there's a tremendous amount of detail here. First, we're going to talk about the ring opening of strong nucleophiles. The easiest way to remember if you have a strong nucleophile is look for an atom that has a formal charge of -1, okay? Strong nucleophiles are also going to be strong bases, but they're going to have a -1 charge on the nucleophile. Examples of this include alkoxides. We write an alkoxide NaOR or RONA, and that, remember, is a formal charge of -1 on the oxygen, and the sodium ion is simply a spectator ion that's not involved in the chemical reaction. So those are called alkoxides, okay? The other class of compounds here that we have are cyanide. So if you have NaCN, that is basically a sodium ion, right, which is a +1, and then cyanide, which is a -1 polyatomic ion. And the carbon is nucleophilic here because it has a formal charge of -1 on the carbon atom. So we just call that cyanide. So interestingly enough, that forms a carbon-carbon bond. Another source of nucleophile are something simple like this, NaSH. That's a sulfur atom there. And so this is very strongly nucleophilic at the sulfur atom, okay? Phthalates and sulfur with a negative charge are extremely nucleophilic, much better than oxygen. You see, oxygen is a very electronegative atom, and the electron cloud is very small compared to a sulfur atom, which is further down in the periodic table, and it's more fuzzy and more polarizable, and so it has a greater nucleophilicity compared to oxygen. We saw this trend also with the halides. Iodide is the largest of the atoms, very polarizable compared to chloride, which is smaller. And so these large fuzzy groups are polarizable and have a greater reach as they're forming a bond to carbon. Okay? Grignards also are very strong nucleophiles, and the reason why is because you have a carbanion with a negative charge. Okay, these are carbanions, and they definitely have a formal charge of -1. So carbanions come from Grignard reagents. They can also come from acetylides, okay? Lithium aluminum hydride, LAH, is a source of hydride, okay? Hydride. And so the hydride there is a very strong nucleophile when it comes from lithium aluminum hydride, but you can only use LAH. Okay, so let's take a look at some of these chemical reactions now. Okay, so if you take an epoxide and you treat this with sodium hydroxide in water, you'll form ethylene glycol. Okay, the curved arrow reaction for this involves, right, so we could call this basic or strong nucleophilic conditions because we have hydroxide in solution. So we want to use the basic curved arrow reaction mechanism for this. For that curved arrow, you first attack with the nucleophile. The nucleophile attacks the epoxide. Why is the epoxide so reactive? Two reasons. It has ring strain associated with it. Okay, a three-membered ring has quite a bit of ring strain. Remember, the ideal bond angle for an sp3 hybridized atom is 109.5. These bond angles are significantly less than that. The other reason epoxides are reactive towards strong nucleophiles is that there's significant polarity of the carbon-oxygen pi bond. So you can just think about electrostatics and opposites attracting. This nucleophile is attracted to this electrophile by the partial positive charge on the carbon atom. When attack occurs, I like to label my individual steps with a simple abbreviation. You get an alkoxide that's present here, okay? In step 2, we're going to have protonation occur to give us the neutral diol or ethylene glycol in this very specific case. So here's where we use the reaction solvent. It could be methanol or ethanol or water. Here it's just water. And so you want to pick up a proton from the solvent, and that's going to give you ethylene glycol, okay? So when you have a base reacting with an epoxide or a strong nucleophile reacting with an epoxide, it's a two-step procedure. It's first attack and then protonation, okay? The protonation does not occur with H+. It occurs with the neutral solvent that's present. So ethylene oxide is quite reactive and can also react with sodium methoxide in water. In this case, we are using methoxide as the nucleophile right here. And so that's going to install this methoxy group here. Okay. You could probably call this molecule 2-methoxy ethanol. All right, so how does it work? The same procedure as before. We have methoxide, which is our formal charge of -1 on the oxygen, which makes this a strong nucleophile. It attacks the ethylene oxide, which is a very potent electrophile, and that gives us this intermediate here. And we form a new alkoxide, which then becomes protonated to give us the final neutral product in the presence of water when that's added, okay? Now, let's look at yet another example. Here's sodium cyanide in step 1 and then water in step 2. Sodium cyanide is going to install this nitrile functional group. Whenever you have a carbon-nitrogen triple bond within your molecule, we call that a nitrile functional group. The nitrile functional group shows up a few times in this chapter as well as subsequent chapters, so it's a good idea to memorize and recognize that functional group now. The procedure involves cyanide, which has a formal negative charge on carbon, attacking the epoxide at the carbon atom, giving you a new carbon-carbon bond. The alkoxide then, after it's formed, is reacted with water in a second step to give you the neutral product here. Okay? So again, these are attack, then protonation. Let's look at another example. Here we have NASH, so to speak. This guy here, we totally ignore the sodium ion. It's just a spectator ion there. The curved arrow reaction mechanism involves this negatively charged nucleophile attacking this epoxide. This gives us, after the first attack step, this alkoxide, okay? And this will react with water to form the neutral thiol slash alcohol over here, okay? So that's a protonation step, all right? Grignards, remember again, contain a carbanion, a carbon with a negative charge. And these can add various R groups to the organic epoxide that you have. Isopropyl, a phenyl group, whatever you desire. Here we're just starting out simple, and we're adding a methyl group to the left carbon of this epoxide. The curved arrow reaction mechanism is going to include drawing out your R group. In this case, it's a methyl group. So we need to make sure it has a negative charge there, and this is going to be attacking the carbon on the left to give you one propoxide. And then after protonation, we are going to get this propanol, okay? It's kind of a lame synthesis, but it illustrates the reaction conditions and the mechanism, okay? So first step is attack, second step is protonate, all right? How about lithium aluminum hydride? As I mentioned, sodium borohydride, lithium aluminum hydride are sources of hydride. Lithium aluminum hydride is the one that can only be used for epoxides because it's a strong enough reducing agent. The mechanism is going to involve taking your hydride, attacking one of the two carbons of your epoxide to give you ethoxide, and then after that we add water, and you know the drill by now, I believe. You can protonate that to give you the ethanol molecule, okay? But we've added hydrogen here, okay? So this is rather useful. Now let's talk about the regiochemistry of this ring opening. Regiochemistry comes from the word region. Where in the molecule is there going to be attack? So for example, if we have something like this, and we treat this with a negatively charged nucleophile, followed by addition of water, we see that the nucleophile attacks the less substituted carbon atom. Okay, attacks the less substituted carbon atom. Now the reason why is because it goes through an SN2-like transition state. I'll just say mechanism here. And remember that you have a tertiary carbon here, and you have a primary carbon here. So if you have a negatively charged nucleophile, that's going to prefer to attack the less sterically hindered carbon atom. And that's why the nucleophile attacks the right carbon, which is more sterically accessible. It's easier for that nucleophile to get in there. There's more wiggle room. There's more space for it to get in, okay? So that's what you're going to do, okay? So the strong nucleophiles, this is, basic or strong, are going to attack the less substituted carbon atom. Okay, and that's a key thing to remember. Okay, and it's based off of SN2. So if you remember a lot about SN2 reactions, this might kind of be very familiar to you. That's the goal. All right. So the other thing we want to talk about is stereochemistry. All right, stereochemistry. So for example, if we have a molecule that looks like this, Okay, let's take this epoxide here and let's treat this with a strong nucleophile followed by water workup. So now for the sake of this conversation, let's choose to attack this carbon on the right. Now I know both of the two carbons of the epoxide are both secondary, but let's choose the one on the right just to discuss things here, okay? So if there's going to be a nucleophile that attacks this carbon right here and kicks off the oxygen there as the leaving group, you're going to have inversion of configuration at that yellow dotted carbon atom, okay? So this is where you're going to have inversion of configuration. Okay. Now remember that in SN2 reactions, you have backside attack. Okay. Now, the nice thing about epoxides is that we draw the oxygen-carbon bond, generally speaking, in the plane of the board. In this case, I have. So what we want to do is approach this leaving group from this direction. So the intermediate, the final product, in fact, is going to have your nucleophile down here on the bottom right side of the screen. And that's because it's attacked from the opposite side as the oxygen that leaves, okay? Now the methyl is still on a wedge. It's still coming out towards us. And the hydrogen is still on a dash. Okay? But the nucleophile and the oxygen have appeared to switch places. Okay? The oxygen used to be towards the upper left-hand corner of your screen, and now the nucleophile is towards the lower right side of the screen. If you want to spend the time, just make the nucleophile be methyl, for example. If you want to spend the time figuring out if it's R or S, you'll see that it goes from S to R. Okay? The left stereogenic center, we'll dot it here with the green, does not invert with the stereochemical configuration because there are no bonds being broken, there are no bonds being formed to that green dotted carbon. So the OH is going to still be on top of that carbon. The methyl group is still going to be on a wedge, and the hydrogen is still going to be on a dash. Okay? So the key thing here is that we have inversion on the right stereogenic center that's being attacked. But on the green dot here, it's being retained. So we say retention. Okay. So you have inversion of configuration on the actual carbon that's being attacked. Okay. Now, the other is retained. Okay. All other stereogenic centers in the molecule are going to stay the same. Okay, so there's a lot of detail here. You need to remember the reagents. If they have a -1 formal charge, they're going to react by the basic or the nucleophilic reaction mechanisms. They're going to attack, then become protonated. For the regiochemistry, we discussed how these strong nucleophiles are going to be attacking the least substituted carbon atom in your epoxide. Finally, for the stereochemistry, we see that because these react by SN2 reaction mechanisms, they are going to cause inversion of configuration at the carbon atom they are attacking, but all the other stereogenic centers in the molecule are going to retain their original stereochemistry. Okay, so there's quite a bit of detail there. Let's go ahead and look at some examples of this. So problem 17 in the Klein's textbook asks us to predict the product. and also draw a mechanism. What I would like to do is draw a mechanism, and when I get to the end, that'll be the product, okay? So in part A, we have an epoxide. We have a primary carbon on the left, and we have a secondary carbon on the right. When I look at my reagents, I see PHMGBr. PH means phenyl, and MGBr, we just, write it out like that, okay? So this is a strong nucleophile. It's basic. It has a negative charge on the carbon. It's a carbanion. And so we want to attack the less substituted carbon, which is on the left. So the reaction mechanism is going to look like this. I won't draw the C and the two dots there. I'll just draw a negative charge on that carbon. And that's going to attack this molecule here, okay? And it's going to attack the left carbon, and that's going to give me a phenyl group, I'm going to place a dot on that carbon so I can keep track of the carbon counts in my molecule, okay? And what I'm going to have over here on the right carbon is a methyl group still on a wedge, because I know that there's no attack happening at that carbon atom, so it's not going to be inverted, okay? Next, that alkoxide is going to react with water to form our neutral alcohol product. And we call that P for protonation. And that's going to give me the molecule here. So that would be predicted to be the final reaction product. Some students sometimes ask me, what about this stereogenic center that's being attacked? Do I need to show wedges or dashes because it's supposed to flip from S to R, R to S? Well, the dotted green carbon here in the original molecule, it is not a stereogenic center because we have two hydrogen atoms. Remember, for a stereocenter, you need 4 different groups to be on that carbon atom, okay? A similar thing would happen in part B, but instead of phenyl magnesium bromide, we have sodium cyanide. So what would that look like? Well, here's our epoxide. It's a nice chiral molecule with a methyl group here. And if we treat this with cyanide, so sodium cyanide is a source of negatively charged cyanide ion. In the first step, we're going to have nucleophilic attack of the cyanide. And you might be wondering, why do I write it this way, N then C? Because there's a carbon-carbon bond being formed, so I want to draw the C next to the other C. I don't want to write it CN and then draw a line to the carbon, because that would imply that the nitrogen is forming a bond to the carbon. In the second step, I want to protonate this and that's going to give me this neutral nitrile. There's an alcohol over here, and there's a stereogenic center. There's a methyl group here. Okay? So this is how you think through these problems. Let's continue onwards. Problem 17, E and F is something I would like to demonstrate now. When we look at these molecules, you need to look at the epoxide functional group and realize that that's the very reactive functional group present in this molecule. Look at the reagents and recognize that we have sodium thiolate here. So SH minus is a very strong nucleophile. This is the one that's going to be attacking the less substituted carbon atom, which is on the right. We need to remember to invert that stereogenic center. We can do so very easily if the carbon-oxygen bond is drawn in the plane of the board, which is what's happening here, okay? The CO bond is just a line. So all we need to do is take the nucleophile, attack our epoxide, and that's going to give us a molecule where the left stereogenic center has not changed. the right stereogenic center has. We need to draw the S-centered nucleophile on the bottom right, whereas the oxygen was kind of going towards the top left. Whereas this methyl group, the methyl group is still coming out from the computer screen or phone, however you're deciding to watch this. In the last step, as usual, we have protonation that occurs. Our alkoxide is going to become protonated with neutral water, large amounts of it present, and that's going to give us the final product. Takes a bit of time to draw. There's all those little wedges and dashes in there. Okay, so that's the product there that we get from that transformation. Let's take a look at part F. So we have a stereogenic center on the left, which is more substituted. We have a stereogenic center on the right, which is less substituted. Here we have secondary, here we have tertiary. So we know that LAH is a nucleophile, it's hydride, which is going to be attacking the the right stereogenic center. When it attacks the right stereogenic center, what happens? Okay. Well, let's draw this out here. So we have an attack step. And we want to draw the hydrogen coming from this direction, okay, the bottom right. The methyl group is still coming out of the screen. And the hydrogen that is originally present on the organic molecule is going behind the screen, okay? So that's the reaction intermediate. Now remember, we don't need to draw these hydrogens. And in fact, this is now no longer a stereogenic center. So it's not a stereocenter. You see, when we add hydride to this epoxide, we now introduce two hydrogens on that right carbon, which kind of negates its stereo, its asymmetry, okay? Now what we need to do here in the second step to finish this up is to react this with water, and that's going to form a molecule that has a stereogenic center on the left, but there's no stereogenic center on the right. This is just an ethyl group, so CH2, CH3. Okay, it's an ethyl group. So that's going to be the final molecule there. Okay? So some of these reactions can be tricky. Review your stereochemistry very carefully when you start working on these, okay?